Welcome to Tone Academy. I'm Chandrasekhar Vadlamani. I'm the senior faculty for all, and I've been mentoring for the top 10 ranks of IIT JEE. All my colleagues will be lecturing for you and for the exams, what you'll be writing almost immediately. You must understand, I appeal to all the students, please do subscribe because we'll be following a sequence for you, right? And this will be really helpful to you. Thank you. Very good morning. Welcome aboard. This video is exclusively shot for those students who are writing their immediate exams. Let me list those exams. You will be writing the first slot of, JEE mains. Then you have the second slot of JEE mains, and followed by that, you will be having your EAMCET exam or any pre-engineering test. So I request all the students to please follow the sequence in which we are actually teaching. And I want every student to understand that each subtopic there will be questions followed and linked to the pre-engineering tests. Please understand. So that's my appeal to all the students is, please follow these lectures without fail. And all the students who are writing NEET or any pre-engineering tests must be following, because I'll be following a sequence, and this sequence I am actually dividing into subtopics, and this subtopics, after finishing that, you will be linked that to a pre-engineering test, say mains, NEET or whatever. So it's exclusively important. These lectures are important. Don't go here and there. You can just sit, relax in your room and just listen to these lectures as far as chemistry is concerned. Well, I am Chandrasekhar Vadlamani. Without wasting time, let's go in for the first lecturing of chemistry, that's atomic structure. So you can look here, this is the Roman number. So what I will do is, I will divide all the topics into Roman numbers. Each Roman number is a subtopic, and this subtopic, once we finish the concepts, we will be writing and linking this to the pre-engineering tests. So let's start our lectures. This is dual nature of light. Well, I always feel that, atom is invisible. It's an invisible quantity. When atom is invisible, there is so many things done inside the atom. We are not cutting with a knife. The atom is not cut with a knife. But people were able to check out what is there inside the atom. So it is surprising to me even now how they were able to penetrate into that atom and check it out what is there, because atom is invisible. You can't hold it in a hand and you can cut it with a knife. How is that possible is the issue. And let me tell you that, when we speak of dual nature of light, it is actually giving you a hint. But earlier, before 1919, this is what is the theory which was prevailing. And look at this. Look at this. This is corpuscular theory. Corpuscular theory, meaning that light is absolutely deemed to be a particle. Absolutely. No other way of dreaming about what? Light. So light is basically consisting of corpuscles. Corpuscles meaning this is nothing but particles. This is nothing but particles. Now my issue here is, if you just hang on to light being a particle, then there are so many other things which you are unable to explain. Let me tell you some of this. Let me list out some of the properties of light. Now some of the properties of light are, one is diffraction, refraction, interference. And what are these? If you ask me, interference, diffraction and refraction, if you ask me, these are all the properties of light. And let me tell you, if any student is dreaming or hanging on that light is just a particle or a corpuscular theory which was prevailing at that particular point of time, then let me tell you that you will not be in a position to explain neither diffraction, neither refraction, nor interference. Now, these things are left out of the purview of the theory which was prevailing earlier. That is nothing but the corpuscular theory, you must understand. So my contention is basically, understand that if you are not going and just hanging on to a Newton's corpuscular theory which was available at that point of time, there are several properties of light which you are not able to explain and will not be able to explain. Not only you fail, but miserably fail in explaining the properties of light. So if someone is asking me what exactly is refraction, diffraction or interference, then prima facie I can tell you that these are properties of light. And these are the properties of light you will not be in a position to explain. Just hang on to what? Light being a particle. So we need some extrapolation in this regard. And let me tell you that this is the first subtopic which I'm taking, and there are questions on the applications of what dual nature of light, and the Planck's quantum theory also comes into effect. And the applications of the Planck's quantum theory are the questions in JEE mains. So let's go into the theory first. Now what exactly is this dual nature of light? The dual nature is something like this, which was first proposed by Planck. First proposed by Planck. And I would like to tell you, this is something which revolutionized, I would like to use this word, revolutionized physics. When I say physics, I take an integrated approach. You please understand, this revolutionized science rather. When Planck was first proposing his theory, discarding only light being a particle, he wanted to tell something else. And let me tell you that this revolutionized physics. When I say someone has revolutionized science, I mean that this was proposed for the first time. If someone is proposing it for the first time, that's when I call it to be revolutionized physics. And let me tell you that this theory, when he was contending for his Nobel Prize, it's an 18-hour marathon lecture when he was inviting all the scientists in the room, and this is what is proposed. And I think when I say revolutionizing physics or science, what exactly is the statement which he wanted to propose? And here is the proposal what he wanted to make. Let me put things in perspective. What we are trying to do here is, there was one theory which says that radiation or light is just a particle. If you just hang on that it's a particle, there are so many properties of light which you will not be in a position to explain. So when these things are left out, a theory, the people are craving for a theory, for an explanation, for a convincing theory where we can even explain the other properties of light which this Newton's corpuscular theory is unable to explain. For that, there is one theory proposed by Planck which revolutionized physics. When I say revolutionized physics, what is the statement which is making, which is for the first time? And here is the revolutionized statement which I quote. Watch here. Watch here. This is the statement which he is making. Look into this. Radiation is shot out. It is shot out. When I say radiation, synonymously I mean light. So the students must understand, when it's a radiation, it's a comprehensive thing. You can just imagine, dream it to be a light. When he is proposing something about light. Now why we should have the first subtopic to be radiation? As I told you, atom is invisible. You're not cutting with a knife. But people have checked, there is a regular arrangement inside an invisible atom. When you have a regular arrangement, people have done so much research inside the atom. What is there? How do we do that? We are not cutting with a knife. So it is basically the radiation which is actually passed into the atom to check some photographs of what exactly are there inside the atom. So when radiation is like a tool for science, basic tool for science to understand the environment which is there inside the atom, I think every science student must know some theory with regard to what? Radiation. And half, as I said, it is only a particle. Now we are extrapolating that into something else such that we can explain all the properties of light. And in that case, hence I propose a revolutionized proposal proposed by Planck. And here is the revolutionized proposal which I quote. Radiation or light is basically shot out. It is shot out in the form of a gun. When I say shot out, you can imagine that it is shot out from a gun rather. So radiation is shot out in form of, I would like to underline something here, in form of packets. When I say packets, you, me, or anyone will first visualize in our mind that packet is basically a particle. No one will dream anything else. When I say radiation, suppose if this is the source which is giving out radiation. Assuming that this is the source which is giving out radiation, then Planck says that it is actually shot out in the form of packets. And each packet, when someone wanted to revolutionize, suppose visualize that, I think they should be first dreaming it to be a particle. Now, this is not finished. If this is a particle, there is already a theory. What is the new you are telling? So understand that radiation is shot out in a form of packets, in form of quanta. Let me tell you, this is quanta. Now here is a word for a packet. Packet seems to be a normal English word. For that, the technical word is quanta. Look into this. Why it revolutionized physics, I would like to explain. But look into the proposal what he is making. Radiation or light is shot out. It is shot out in form of packets, in form of quanta. So the packet must be visualized to be a quanta in a, look into this. I would like to underline one more word, in a discontinuous fashion. When I say discontinuous fashion, suppose if this is the source, then it is packet after packet, packet after packet, packet after packet, you must understand. So, if I read it again, radiation shot out in form of packets, which is called quanta, in a discontinuous fashion. Now, as I told you, packet should be visualized in form of what? A particle. Then what is revolutionizing here is the issue. Watch carefully here. This is not finished, it's a comma. I'm completing the statement now. Discontinuous fashion. That means that these are shot out one packet after packet, one packet after packet. That's what I call it to be a discontinuous fashion. And when someone is asking you, when you're shooting out packets, natural question arises in the mind of anyone that what is there inside the packet? That's a natural question which kicks in. Please understand that when someone is shooting out packets and someone is asking me what is there inside the packet, here I quote, and I quote this. Discontinuous fashion, comma, and see what he's telling. Energy content in the packet is called quantum. And I want to warn the students or whosoever is listening to this lecture, please understand that you cannot substitute quanta for quantum. Let us have a clear idea. Quanta is a packet which is shot out by the source of the radiation. And if someone is asking me what is there inside the packet, then I call that to be quantum. So let me be clear, quantum is the energy content which is there in the packet. Quanta is nothing but the packet, you must understand. Now, if the energy content is quantum, then naturally one more question arises. So three things what you're telling here. Three things. One, radiation is shot out in the form of what? Packets. And the packet is given a name called quanta. And someone is asking me, what is there inside the quanta? It is nothing but the energy content. And the energy content has a name which is called quantum. And I warn the students not to be complacent in just substituting quanta for quantum. Quanta referring to a packet, and quantum is nothing but the energy content. So next, the one more question which arises, if someone wanted, you cannot make gestures. If someone is telling you that packet you have energy, you can't show your hands and say this much energy, this much energy, this much. These gestures won't work. Someone will ask you, yes, how much is the energy content? How to measure it? How to measure it? And I draw the attention of students. As I said, it revolutionized physics. And here is a small part which I am writing it. And this is what is revolutionized physics. Watch carefully here. And there is a question which is following, that what is there inside the quantum? It's nothing but the energy content. Someone asked me, how do you measure it? How do you measure it? How much is the energy content? You can't show your hands. You can't make gestures. So how much is the energy content is given by the formula. E is equal to h nu. Look at this cute formula. E is equal to h nu. This equation, you need to use it if someone is asking you how to measure the energy content in the packet. Now, if I look into this postulate, I have written it revolutionized physics. If any student is actually reading this, it looks to be absolutely normal. What is the revolutionary thing here? So let's understand. So it's basically telling that you shot out in the form of packets, is quanta, energy content is quantum, and is governed by the formula E is equal to h nu. Where is the revolutionary part? And let me now draw the attention and explain where exactly is the revolutionary part you must understand. Now, let us see why do we write it revolutionized physics? What is there in this statement which revolutionized physics? Let us understand here. And here I explain this to you. Watch carefully. I draw the attention of every student now. Where is the revolutionary part? Look at this. Look into this. Initially, watch carefully. Initially in this statement, you said that energy is shot out in the form of packets. Initially, we visualize, well, understand here. Initially, when someone is telling that a source has been shot out, shooting out radiation, initially we visualize this packet to be a particle. You must understand. This is a particle. So initially when we are dreaming about something has been shot out, I think everyone will dream it in the form of what? Particle. Now the issue is, look into this issue. Look into this issue. Look into this issue. What is so revolutionary here? When someone is telling it's a particle, and if you wanted to measure how much is the energy content in the packet, if you wanted to measure how much is the energy content in the packet, then look into this. Look into this. I am actually forced to introduce. I am actually forced to introduce. There is no other option for me. I am actually forced to introduce a wave characteristic. I'm actually basically introducing a wave characteristic. And how is that? You said initially a packet, I dreamt it to be a particle. Now, if you wanted to measure the energy content in the packet, then I'm forced to introduce a wave characteristics. And where is the wave characteristics? And look into this formula. Look into this formula. E is equal to h nu is the formula which you need to use it to find the total energy in the packet. And what is happening here is nu which you are introducing to measure is nothing but frequency, and frequency is a wave characteristic. You must understand. Initially everything was fine. Initially it was a particle. So we all are dreaming about to be a particle. Packet is a particle. Now when you're coming to measuring how much is the energy content in the packet, I'm actually forced to introduce a formula which is E is equal to h nu, where nu is frequency. And let me tell you, let you also recollect, frequency is a word used and it is a wave characteristic. To determine the parameters of a wave, we use frequency. And when this proposal was made, there are all learned persons in the Nobel Hall where he was contending for the Nobel Prize. So many people, so many learned persons, scientists, so many people were sitting. And what he's trying to tell is, initially, yes, we dream it to be a particle. When you wanted to measure how much is the energy content in the packet, I'm forced to introduce a formula which is E is equal to h nu, and that nu has a wave characteristic. It has a wave characteristic. Now, what do you mean? Where is the revolutionary? If you ask me, sir, you are telling all this, we followed this, you are telling that radiation is shot out in the form of packet, and if you wanted to measure the amount of energy in the packet, you are introducing E is equal to h nu. Fine, it's fine, but where is the revolutionary thing? Where is the revolutionary thing? Well, I would like to explain. You know, people, learned persons who are actually sitting in the room, they understood it. They understood. Now, where is the revolutionary issue? Here is the revolutionary issue which I would like to quote. And before I rub it, as I quote, these are the packets, and the packets are called quanta, and what is there inside the packet is nothing but quantum. And if you wanted to measure how much is the energy there in the quanta, then that's nothing but E is equal to h nu. And the initial thing is we visualize it to be a particle, but I'm forced to introduce a wave characteristic. This is new. And now I'm explaining how this entire thing has revolutionized what? Science or physics. Let me tell you this. Now, what is there so revolutionary in the statement which was proposed by Planck? Let me tell you, if you are a learned person, I think they have understood by this time when he was proposing within seconds. Now let me explain what is so revolutionary in this. Watch carefully here. Now what we said, the packet, here I write it again, the packet that is shot out, then it is visualized as particle. Now someone is asking me a question, how much is the energy content? Energy content in the packet. I write it for you. You look into this. Packet shot out, it's visualized to be a particle. And someone is asking me what is energy content in the packet. Then this is, I'm actually forced to introduce I am forced to introduce this formula E is equal to h nu, in which nu is a wave characteristic. You must understand. Initially, we started off with a particle, and then we wanted to measure how much is the energy content. I'm actually forced to introduce a wave characteristic that is nothing but frequency. Nu is nothing but frequency. You must understand this. So there is something confusing here. And if you are a learned person by this time, you would have understood this. If you have not followed, then look into this revolutionary aspect. And let me tell you, I would like to write this. This is proposed for the first time. This is revolutionary aspect which is proposed by Planck. You must understand. This is a revolutionary aspect which is proposed by Planck. And what is so revolutionary here? This is introduced for the first time. What do you mean by this? What do you mean by this? You must understand this, that I am actually privileged to write this. I'm actually privileged to write this. I have done this so many times before, but really I always be privileged for this guy, Planck, because it was told for the first time, and I take this privilege in writing this revolutionary aspect which was proposed by him. And let me tell you that he for the first time, I draw the attention of everyone, please. He for the first time, and I would like to underline this, he for the first time, trying, I call it to be trying because he is still proposing it. He is contending for the Nobel Prize, he didn't get it. You need to propose, you need to convince the crowd, and then if they feel emotional, they will throw the Nobel Prize onto you, right? There is something left. So what I mean is he for the first time, trying to introduce dual nature to light. He for the first time trying to induce dual nature to light. Now, when someone is proposing dual nature to light, I actually recollect there was one theory which was pre-existing before this fellow who says that light is just a corpuscle or a particle. It is just a particle. Now this fellow comes in and says it has dual nature of light. Now it has a dual nature, then what exactly is dual nature? He is telling is basically the light or the radiation. It has dual nature, meaning it can behave as a particle as well as a wave. It will behave as a particle as well as a wave. When he proposed this, there was a stoic silence over there inside the room where he was contending for the Nobel Prize. Because it was the first time. It's so revolutionary. It is so revolutionary. He is telling that light has particle, it has a particle nature as well as what wave nature, which is actually there here. You look at this. When I proposed packet, initially I was visualizing it to be a particle. And when someone asked me how much is the energy content, then I'm forced to introduce a wave characteristic that is new. That's nothing but frequency. So basically in our words, in simple words for the students, you must understand he for the first time trying to induce dual nature to light. You must understand. So that means that light will now possess particle as well as what? Wave nature. When someone is doing it for the first time, you always have abstractions. Even this fellow faced the wrath of the learned people who are sitting there. You know, in the very first bench you have young scientists. When he proposed this, there was actually people who were laughing at it. And let me tell you that they wanted to abstract such that they can extract more out of Planck. And Planck is a learned person, and he came there with all the homework done and contending for the Nobel Prize. And when he proposed this, that light has both particle nature as well as wave nature, here is a first bench scientist who are raising their hands. And they are asking me, oh, it possesses both wave nature as well as particle nature. Then we wanted to know, very clear question, Mr. Planck, here is a question to you. They wanted to ask him, when does light behave as wave? When does light behave as particle? The seconds he proposed dual nature to light, there was some intimidation from the crowd, and they wanted a correct answer. You cannot say you have both dual nature and run away from the room. You cannot run away from the room, but just by contending that it has a dual nature. Now people will ask you, when does it behave as a wave? When does it behave as a particle? So that's a natural question which has come out, but not in this decent way as I'm telling, because scientists are cruel and they wanted to actually intimidate this fellow by asking this. You know, when people were intimidating constantly, well, if you actually look into the research papers, you don't get this in textbooks, but once you do the research papers, well, he was seriously joking at that point of time, because constant intimidation, you get angry. You got angry. So, when people were asking, when does it behave as a wave, when does it behave as a particle, look at Planck's wordings, which were the exact wordings which I wanted to present it to you. He was basically telling that on Sunday, Monday, Tuesday, it behaves as a particle, and the remaining 4 days, it behaves as a wave. Because of the intimidation, this is what is the exact wordings. I'm not joking. I'm not joking. Please understand that these are the wordings used by Planck in the research paper which was submitted for contending for the Nobel Prize. And he's seriously joking such that these fellows can be silenced, and you cannot joke and run away again. You need to convince people. Now coming to the point, when you propose dual nature to light, there should be, convincingly you should be explaining that. You cannot silence the people because they have just asked you the questions. And what is a convincing theory? And I love it. And I love it because the way he'll be convincing, and people got emotional, and the Nobel Prize was thrown onto his face where he was profusely bleeding. And I'm actually on the lighter note, but that's what exactly happened. And I love the way he has convinced that light has dual nature. And these are the statements which I'm writing now. They are absolutely convincing by telling that light has dual nature. And at this point of time, of course, yes, light has dual nature, and we are all also convinced, right? And here are the statements which will tell you that light has dual nature. And before I tell you, write the 4 statements, synonymous statements which are convinced for the dual nature of light, here are just a recap of what we are doing, right? Understand that when you propose a packet, everyone will visualize to be a particle. You must understand. When someone is asking what is there inside the packet, it's energy content, and you're forced to introduce E is equal to h nu, where nu is a wave characteristic. You must understand. So he's basically for the first time trying to introduce dual nature to light. That means that the light possesses particle nature as a wave nature. Then naturally a question will arise, I want a clear-cut explanation. When does it behave as a wave? When does it behave as a particle? And here is the explanation, and I draw the attention, and I'm privileged to actually tell this theory because it's really a privileged theory, and these explanations are not given in your textbooks. So when you listen to these lectures, it increases the science aptitude and the interest towards science, because the exams what you're writing are also aptitude exams. You must understand science aptitude exams, nothing more than that. Now when you actually say that it has dual nature, and naturally a question will crop up. When does it behave as a wave? When does it behave as a particle? Right? You understand that here is a convincing explanation, and I take the privilege of explaining this to you in the simplest words, and these are the exact wordings of what Planck. This you don't get it in your textbooks. Well, what happens is when you listen to these explanations which are given in the research papers, that increases the interest in science and the aptitude towards science, because the exams what you write are actually nothing but science aptitude exams. The NEET or whatever you are writing, those are aptitude exams. So I take the privilege of explaining, finally explaining that light has dual nature. Look into these statements, man. I just really love it. I just really love it the way he explains. And I take this privilege of explaining this to you. And look at this. He says that there exists. That is a symbol for there exists. There exists great intimacy. There exists great intimacy, right? You must understand. I would like to underline. Great intimacy. And this explanation is given to explain when does light behave as a particle, when does it behave as a wave. You just cannot say that it has dual nature and run away. It's not possible like that. You must explain when it behaves as a wave, when does it behave as a particle, and here is the explanation what he's giving. And each statement what I'm writing is synonymous with the other, and finally he gives a statement which he receives a Nobel Prize. And here is the privileged statements, I call them so. And there exists great intimacy between a wave and a particle, says Planck. Great intimacy, like milk and water. Great intimacy. I would like to add some more ease to the great. Great intimacy between wave and a particle. Now, when you say such statements, there is a question which is prevailing in the room, and people are asking you, when does it behave as a wave? When does it behave as a particle? You can't tell stories. You can't tell stories. And you please understand that when he started off, he is telling again a story. It looks to be a story. There exists a great intimacy between wave and a particle. And even though there is intimidating going on, again asking the same question, when does it behave as a wave, when does it behave as a particle? And here is a second statement, what he is trying to tell. This great intimacy, look into this. I take the privilege of explaining this to you because these are privileged statements. And this great intimacy is leading to indistinguishability. Indistinguishability, I would like to underline. You have such a great intimacy, people are unable to distinguish what is a wave, what is a particle. You must understand. And he's trying to explain this, and people are not interested in this. Again, intimidation started because the question is crystal clear. The question is crystal clear. They wanted to know, when does it behave as a wave, when does it behave as a particle? It's a simple question. You can't tell stories, but still Planck wanted to tell these stories in explaining, yes, there exists a great intimacy between wave and a particle, and this great intimacy is leading to what? Indistinguishability. Meaning you are unable to distinguish where is the wave, where is the particle, because you have such great intimacy. You know, this is again looking to be story. And look into this. This statement, I think it silences the critics forever. Watch carefully. And what is it telling? It is leading to indistinguishability. Thus. Here is the reconciliatory statement. He wanted to reconcile all this now. Thus, he says, and I quote, I take the privilege, I enjoy telling this because this is so privileged, man. This is so privileged. And he says, every particle, and I use a powerful word, and look into this word, and I wanted to underline twice or thrice this. You must understand, every particle is associated with a wave. You must understand. Every particle is basically associated with what? Wave. So from now onwards, when I'm going out as a student, when I wanted to go out as a student, venture out, I'm a science student, I'm flaunting my book, and someone is showing something and asking you, is it a wave or a particle? I think you can slap him. And he will ask you, why did you slap me? Because you understand that every particle is associated with a wave. It's associated with a wave. When I walk like a wave. It is not convincing to you. But please understand that in me, the particle nature is dominating. Whereas in some cases, the wave nature will dominate. But let me tell you that there is this great intimacy. You cannot separate a wave characteristic from a particle characteristic in case of radiation. And let me tell you that I would like to explain this further. I have my own inference. Look into this. The question which was prevailing was, you tell me, when does it behave as a wave, when does it behave as a particle? That was the question. And here is what is a synonymous statement he's trying to explain. Great intimacy. That's number one. Second, you have that, due to this, the consequence is you have indistinguishability. And hence he is making a conciliatory statement that every particle is associated with what? A wave. Now, if still we have confusion, then I have my own inference, and this statement really, finally, it is so convincing that people got emotional, and they were throwing the Nobel Prize onto Mr. Planck, and then onwards, this has become a truth, and you must understand, you and me are convinced right now. And here is the statement which I'm writing it in the simplest words possible, and this will end all the things. Watch carefully here, and so look into this simple statement, what he's telling. And he means, I quote, and he means, look into this, I will be slow here. Whenever, and I draw the attention, please. The entire lecturing is different, and this final thing is the answer for everything in the simplest English possible. Right? And look at this. Whenever you try to explain, I'll be slow here, watch. Whenever you try to explain any property of light, that's radiation. So if you're attempting to explain any property of light, what are the properties of light? Diffraction, photoelectric effect, interference, reflection, refraction. This entire list is nothing but the properties of light. And Planck is telling now, when you try to explain any property of light which I've listed out here, and I quote, treating it as a particle. Well, I would like to make a small change here. whenever you try to explain any property of light treating it as a particle, and you fail in that, and you fail explaining it, you failed because you thought that the light is a particle. So whenever you try to explain any property of light, treating it as a particle, you failed. Then, understand, then, you will pass. And I would like to underline pass and fail here. So when you're trying to explain any property of light, you failed. You miserably failed because you treated it as a particle. Then Planck says, then you will pass by treating it as wave and vice versa. And vice versa, you must understand. So when you are attempting to explain, let me be specific. When you are attempting to explain photoelectric effect, say, you thought that it is a wave. You will not be in a position to explain photoelectric effect. When you treat it as a wave, you failed, you miserably failed. Then Planck says, you will pass when you treat it as a particle. You must understand this. Then what happened was, it was convincing. Then it was convincing. No one was intimidating further. They got the answer. Now coming to our questions, as I promised in the beginning, we will be discussing a subtopic and we will be linking this to the mains exam or any pre-engineering test. Now the dual nature of light which I have explained here, there are questions which will come in exam. What are the questions? Here comes the question which is asked so many times in the exam. So many times in the exam, I would like to write this question which was asked in exam. And watch here carefully. And here is the question. Which of the following equations predict dual nature to light or radiation? Dual nature to light. Which of the following equations given 1, 2, 3, 4 as the options will actually predict the dual nature to light? And of course and if I write it in the options, of course the answer is what? E is equal to h nu. You must understand. E is equal to h nu is the equation which is proposed by Planck, which will predict the dual nature. Because if I basically recollect, what is E? What is E? This is nothing but energy of a packet. Energy of a packet, E, is equal to some constant h into nu, where nu is a wave characteristic, and this is nothing but the frequency, and E, which is a packet or the particle, which I call this to be a particle. And look into this particle and a wave characteristic, both are given in the same equation convincingly, such that you must understand that light has dual nature. And what is this constant? And I think he should take the privilege of this value of h, which is nothing but the Planck's constant, which has a value 6.624 into 10 power minus 27 ergs into second, and that is a CGS unit. You must understand, that's a constant. You need not worry about it. But what is the main thing what I told you today in today's lecture is basically light has dual nature. Why we are worried about light? Why we are worried about light in the first instance? As I told you, atom is invisible. You cannot cut it with a knife. You cannot check it out what is there inside the atom. So there is something which you should pass into it. That's nothing but the radiation. So radiation is like a tool for us to check out what exactly is there, such that you get some photographs of the environments that are present inside the atom. So when you're using radiation as a primary tool to understand what is there inside the atom in atomic structure, then I think you should have some knowledge about what? Radiation. And to that knowledge, let me tell you that there was a theory which was prevailing earlier. So when light is just predicted to be a particle. Now from now onwards, as I said, you flaunt to be a science student, then understand that light has dual nature. It behaves both as a wave and a particle. And now, finally, I would like to say, and I'm linking this subtopic to a question. The first question is, which of the following equations predict dual nature to light? Of course, the answer is what? E is equal to h nu. Here comes the second question. Here comes the second question, is asked so many times. And here is the second question here. Watch carefully here. Which property of light, I write it slow. Which property of light is a direct proof. Is a direct proof that light is a particle. Light is a particle. And here are the options for you. And here is the options. 1, he says photoelectric effect. Photoelectric effect. 2nd, he says diffraction. And 3rd, he says interference. And 4th, he says refraction. And all this. And obviously, the answer is what? Photoelectric effect. And this predicts a particle nature. And I think I will explain how this is a particle nature in our next lecturing. But as of now, please understand that if he's asking a question which is a direct proof that light is a particle, the answer is what? Photoelectric effect. And the remaining three are nothing but the proof for light to be a wave. You must understand. Light to be a wave. Right? So, I would like to end this lecturing by telling few highlights of what we have done today. Such that what is next in our lecturing, you must understand. So I appeal to the students, first of all, don't run here and there. You can just relax in your room, relax, and then follow the sequence of lecturing each and every topic I'll be covering till you actually write your final exams. And just you can get through all the questions because we have been teaching for the top 10 ranks of IIT JEE. And when you listen to this lecturing, you develop that aptitude for science, and then it's an easy understanding for you once you understand the concepts. What we have discussed today, simple. Radiation shot out in form of packets. Packet is a particle, and if you wanted to know what is there inside the packet, it's nothing but the energy. And someone is asking you, well, how much is the energy content? I introduce a formula, E is equal to h nu. So you started off with particle, which is a packet, which is visualized to be a particle. Energy content, I am forced to introduce a wave characteristic. So from now onwards, whenever you fail treating it as a wave, you will pass by treating it as a particle. So light has dual nature, and here are the two questions you must understand. This equation predicts dual nature, and these three, diffraction, interference, and refraction shall be a proof that the light is a wave, and photoelectric effect is a direct proof for the particle. Right? And before I actually leave, to coming back, tomorrow we will be dealing with applications of Planck's quantum theory. Now, what are the applications of Planck's quantum theory? Please do follow me for the next lecturing, and you will be, and as promised, I'll be linking this to the JEE mains exam also. And I thank you for listening to me, and I'll be back for the next lecturing tomorrow. That's applications of Planck's quantum theory. Thank you very much.